the very basic model for the, we started with Bohr's atomic model, basically. We derived the Bohr's atomic model. We looked at it and we saw that energy levels in a system, a balanced system with negative energy, are quantized, basically. And in that case, what we saw is that then, and that's generally true about other kinds of atoms too. So, and then we started bringing these atoms close to each other to form a crystal lattice. And when we started doing that, we saw that due to Pauli's exclusion principle, we cannot have these atoms, these electrons having exactly the same energy level. So the energy levels have to be slightly different. And as a result, you started getting these energy levels degenerating into energy bands. So once you had a very large number, well, I'm going to distribute them. But once we have a large number of atoms, like in a crystal lattice, close to each other, we saw that they basically form energy bands, and we would have energy band gaps. So in the case of the column 4 elements, so we started with silicon or carbon, but in the case of carbon, which was the simplest column 4 element, we saw that when we, at the atomic level spacing, and the lattice spacing of carbon lattice, diamond lattice really, what you have is that you have this band, there are two energy bands. One that's completely full, so it's a filled energy band, and then there was another lower one, the 1s, you didn't care about, and the upper band. And the lower band was completely filled, and the upper band was completely empty. And this energy difference, this gap, is called band gap, G. In the case of silicon, for instance, it's about 1.1 electron volt. And now we saw that, well, this is true only at 0 Kelvin, at absolute zero. As the temperature is raised, what happens is that you will get some electrons, and we saw that this is really controlled by Fermi-Dirac distribution, but we could approximate it for certain cases with Boltzmann distribution. So if you look at the tail of the Fermi-Dirac and Boltzmann, there are always a few brave ones, the hot electrons, that have made it all the way up here. They have enough energy to jump that band gap and be there. And as a result, you have an electron here, or multiple electrons, I guess, and holes, so gaps that are left when the electrons leave, and both of them can carry charge, and therefore can carry current. They both are charge carriers, mobile charge carriers, and carry current. So when you apply an electric field, let's say in this direction, for instance, the holes will move in this direction, and the electrons will move in the opposite direction because they're negatively charged. And now we said, well, or we started the convention that saying, well, we basically really only show the edge of these bands. We don't really show the entire band because we really don't care about the lower edge. So this was the valence band, and this was the conduction band, the edge. So, and then the other thing that we saw is that as is, it's not quite useful, but what we could do is to introduce impurities, or the process of doping. And the process of doping involved introducing other kinds of atoms, most commonly column 3 and column 5 elements. So, for instance, if you introduce a column 5 element like arsenic into this silicon lattice, what you do, you basically have an atom that has 5 electrons in its outer shell. So 4 of them form covalent bonds with adjacent silicon atoms, but the 5th one is very loosely coupled, and we saw that through a calculation. It was similar to the Bohr's atomic model. The only difference was that since the dielectric constant had to be taken into account, and the dielectric constant of silicon, let's say, is around 11.7, let's say ballpark 12, instead of getting 13.7 eV of electron volt energy necessary, you get about 0.1 electron volt. So this energy level for a donor, the column 5 element, is relatively close to the conduction band. So once you raise the temperature, you quickly get electrons released from here without having holes. That doesn't mean that you violate charge neutrality. You have positively charged ions left behind, but they are immobile. That's the difference. They can't move, unlike the holes. And the same way, when we what we did was that we could introduce a column 3 element, like boron. And when you introduce boron here, you would create an energy level here, which basically corresponded to being able to absorb a 4th electron and leaving a hole behind. Now the hole can move, and the ion, the negative ion, cannot move. So that was the basic process of doping, and we'll see how we can use this process to make devices like diodes and transistors and so on and so forth. We'll start talking about that today. Now, the other thing that we did, so And the other thing that we talked about was the carrier distribution. So far, this picture only shows you the density of states. Where you can have electrons and where you cannot, like the band gap. It doesn't necessarily mean, it doesn't tell you how they are distributed. How they are distributed is controlled by this second curve, this orange curve, the distribution that we talked about. And we saw that the distribution governing electrons, because electrons are fermions, is Fermi-Dirac distribution, but we saw that for most practical cases, as long as EF and the energy levels you're interested in are more than 3 kT apart, you can approximate the Boltzmann distribution. Sometimes you cannot. If they're very close, you cannot, and you have to go to Fermi-Dirac distribution, and you can use that, and you can do your calculations. But for 95% of cases, really, Boltzmann is enough. Basically, it boils down to Boltzmann. You have to make that approximation at some point, so you might as well make it up front and make your life easier. So that's what we did. And then there was another calculation that we did, which was a simple calculation, which basically was, what is the probability of finding, what is the number of electrons in an energy higher than an arbitrary energy E1? And we saw that that number was proportional to EF minus E1 over KT, or simply proportional to E1 over minus KT. We integrated this curve from here to there, if you remember. It's in your handout too. So that was the last thing we did, I believe. Yes, actually, one more thing. We also looked at that. We used this, and we derived expressions for the electrons and holes, the density of electrons and holes in any kind of semiconductors. And we came up with these expressions. We basically said N was Ni, N is the density of electrons per cubic meter or per cubic centimeters, whatever. Number of electrons per cubic centimeters or cubic meter. E to EF minus EI over KT. And P was Ni E to EI minus EF over KT. And EF, of course, was the Fermi level, and EI is the intrinsic Fermi level, which is basically where the Fermi level is when there's no doping. Just somewhere in the middle. It's not exactly in the middle of too bad, because the NC and ND are different slightly. Well, they're quite different, so that result, because of the logarithmic dependence, is a slight deviation from the center. But wherever EI is, I mean, it's just some property of the material that you're dealing with. So it's something that you know. And if you look at these two, it becomes very obvious. It's obvious that the product of these two, the density of electrons and the density of holes, is constant. And it's equal to the square of the density of electrons or holes in an intrinsic piece of semiconductor, which are equal. So that's really another way of writing. I mean, kind of more symmetrical way of writing this is like this: NiPi. But since Ni and Pi are equal, because they are thermally generated electrons and holes, when you have no doping, you always show it as Ni squared. Okay, let me ask you a question. Intuitively, why is it that the product of these two is constant, not the sum? Did you expect the product? So how many people did think, I mean, well, obviously the answer is the product, right? But did it appear initially to some of you at least that it should be the sum that's constant? Did anyone have that thought? I had that. But when I first thought about it, I thought, oh, it should be the sum, right? Because I get less electrons here, I get more holes there, right? So it should be some sort of conservation law in my mind. Right? But it isn't, obviously. It is the product that's constant.
Because like N and P are varying exponentially, so.
Well, yeah, well that's looking at the equations and telling. But even more fundamental, why isn't the sum of the two conserved? See, for charge, it's the sum, right? So for instance, the sum of the negative charges and positive charges is constant.
Possibility.
Let's say again.
Because it's some index of possibility.
Probability, is it?
Yeah.
Well, it has something to do with the probabilities. Yes, true. But yeah, but can you kind of make it more, I guess, more intuitive explanation? Okay, let me give you an idea. You see, it has something whole lot of electrons and a whole lot of holes. A lot more than Ni. Right? You can create that situation artificially. Right? You can induce a large number of electrons and holes, and we'll talk about some ways of doing that later. But just imagine that I somehow magically, at some instance, in a piece of semiconductor, I create a whole lot of electrons and holes. One way to do that is shine a lot of light on it. If you have a light with wavelength that has an energy larger than the band gap, you can release a lot of these electrons and holes, generate a lot of electron holes, pairs. Right? So both of them are large. And the sum is still 0. But is that a stable condition? No. Because the number of one affects the probability of recombination of the other. If you have a lot of holes and a lot of electrons, they run into each other a lot. So the probability of recombination, as you pointed out, goes up. So the recombination brings it back. Now, if you had no holes, let's say for the sake of argument, or let's say, that, well, no holes, it can't happen, no holes cannot happen, but it's a way of thinking about very few holes. But let's say no holes. The number of electrons can grow without bounds, right? Because they have nothing to recombine with. So if you have very few holes, then you can have a large number of electrons and nothing will happen because they don't have a lot of opportunities to recombine and disappear. For them to disappear, they have to find a hole. They can't disappear on their own. So that's why it's a product. Whenever you have two species that can actually somehow interact, what happens is that you're looking at the product for the probability of that happening. I can give you an interesting example. In art school, or let's say in engineering school, there are more guys than girls, right? So if someone was prepared to find someone today, for instance, right, I mean, there are fewer people, and vice versa in some other humanities and all those things. So that's one way of thinking about it, right, in general. I mean, non-PC. All right. Was it?
No offense taken on my part.
No, this is the fact. This is the truth, right? Look around you. Okay. All right. So this was what we said last time. Now let's talk about. Let's continue our discussion. So far, we haven't talked about the movement of the carriers inside the lattice, right? What we've done, we've talked about the density. But now the question is, well, how do they move? There are a couple modes of movement in the lattice for electrons. One, of course, is this random thermal movement. Right? Because we know that at temperatures above 0 Kelvin, it's what you have is that you have a certain number of electrons released. And what happens is that you basically have these electrons that have a lot of energy. Now the question is, how fast do they move, first of all? What do you think is the random, let's say a piece of metal or semiconductor, let's say. What do you think is the speed of electrons when they have this random thermal movement? Take a guess. Just I'm looking for an order of magnitude. Any thoughts? Come on.
The velocity at any time or the net velocity?
The net velocity. What do you mean? No, I mean, how fast are they moving around? Random thermal movement.
10 to the speed of light.
10 to the speed of light? 10 to the speed of light. Yeah. Okay, also it's very high. Yeah, that's true. Yeah, actually, I've had cases where people say, well, yeah, that must be about, a millimeter per second or something. So, but let's find out. Let's find out what it is. Let's do it kind of a more approximate, a more accurate calculation. How will you calculate that? Well, you first have to know where the energy comes from, without looking at the handouts, of course. You can read the handouts later, right? So that's interactive. So where is the energy? The energy is thermal, right? What is the thermal energy of an electron in the lattice? If the lattice is at temperature T. What is the energy? Can you tell me? Is there some theorem or principle of physics that tells you what the energy is? That's the beauty of temperature. See, that's a very non-trivial thing in my opinion. That the temperature alone allows you to calculate what the energy of each part of average energy. Expected value of the energy of each particle in the lattices. Extremely non-trivial, but that's very useful. That's the basis of the fact that you can actually define a parameter named temperature and the whole thermodynamics that comes after that. But, so what is the energy of an electron at temperature if you have a lattice that's at thermal equilibrium at temperature T? How do you determine it?
Boltzmann constant times center.
Right. Well, something times that, right? So that's the kT. Half kT is the energy of each degree of freedom. So in any system in thermal equilibrium, each degree of freedom, and it doesn't have to be a mechanical degree of freedom, it can be an electrical degree of freedom, in fact. We have an example of that later. But each degree of freedom takes 1/2 kT of energy on the average. So what is the energy of an electron? 3/2 kT, right? Because you have 3 translational modes, X, Y, and Z. So the energy of the average energy of an electron is 3/2 kT. And that's kinetic energy, right? So that's equal to 1/2 m. I would use m star, that's the effective mass of the electron in the lattice. V squared. So that's the root mean average. Okay? Now, so what happens is that you have to remember, this is a different kind of average from the average velocity of electrons. But since we are interested in an order of magnitude kind of thing, we can look at it, we can use it. Right? So what does that tell me? That tells me that I can say V is approximately, since this is the average V, I'm replacing it with the root mean average, is something like square root of 3 kT m star. Right? And let's see what's the bulk. Yeah, the order of magnitude. So it's 3. What is K? Boltzmann constant? 1.38 10 to the minus 23. You guys should know these. What are the units? This is energy. So what are the units of K? Joules per Kelvin. Times, let's say 300 Kelvin. And divided by, what is the mass of electron? Well, the effective mass of electron is about a quarter of the free mass of electrons. So, say, so the free mass is about 9.1 10 to the minus 31. So this is about ballpark 2 10 to the minus 31 kilograms. Okay, so what is that? So that's the 3, 3, 1. So that's almost a 10. So that's 10 to the 3. That's 10 to the minus 20. And so that gives me approximately 10 to the minus 20 joules divided by 2 10 to the, let's drop the 2. So it's 3 approximately. 10 to the minus 31 kilograms. That's 10 to 11, 10 to 11. Okay, so that's 20. That's 5 to the 11. So that's 5. Let's keep it 2. That's easier. So the 5 10 to the 10. So let's say 5 is 4 approximately. Is 2 10 to the 5 meters per second. How many miles per hour is that? Come on. Ballpark. That's 500, close to 500,000 miles an hour. 800,000 kilometers per hour. That's fast. Really fast. Inside, in a semiconductor, that's the kind of speed you have. Now, the significance of this, it means that electrons are moving extremely fast. This mess of this kind of cloud of electrons, this swarm of electrons, moving around very, very quickly. Very, very quickly. And that's why thermal equilibrium happens so fast. And in fact, that's why electronic devices can be so fast. We'll see that this is actually this random thermal movement that's the basis for operation of PN junction diodes and BJTs. It's because of this random thermal movement, and it's because of the fact that it happens so fast that these devices can switch so fast. We're actually riding the tail of this really fast high speed of electrons. Okay. So that's what we call the diffusion. I mean, people call it diffusion, this random thermal movement. The movement of electrons due to this random thermal movement. And you can imagine it can happen very quickly. If you have more, all of a sudden, if you create a situation where you have more electrons on one side and less electrons on the other side, right? These electrons are moving so fast that very quickly they basically equalize the situation. They go back and basically reach thermal equilibrium extremely quickly. And that's very, very important to consider. But now, on top of this random thermal movement, we can also introduce a second mode of motion, which is when we introduce an external field. So if you have this electron that's moving like crazy, right, going around, and then you can introduce an electric field. So let's say you have an electric field in this direction, right? So what that does is that between different collisions, and you can imagine these collisions happen very close to each other at the time, right? Because they're moving so fast. So something moving at 500,000 miles an hour within a, kind of a micron piece of semiconductor, you can imagine that it will hit something very quick. Even if there were not other atoms in the lattice, and it will hit the boundary, it will hit other atoms most of the times. So this mean scattering time is called actually, the average time between two collisions, or tau c, is extremely short. In fact, for an intrinsic piece of silicon, you can calculate it, and it's less than a picosecond, something like half a picosecond, for an undoped piece of silicon. And if you dope it, it will become even smaller. But so now, what happens is that when you have this movement, which is this electron is having a lot of velocity, right? The speed is very large. I mean, it has a reasonable momentum. So once you introduce this electric field, what you actually do, you deviate its trajectory a little bit. It will be in this direction because the electron is negatively charged, right? So then it makes another collision. Of course, it won't be in the same. It doesn't have to scatter in the same way, but just for the sake of argument, I will show it as the same scattering. But then between here and the next scattering, it also gets deviated a little bit. And then between here and the next one, it gets deviated a little bit. And so there is a slow shift in the location of the electron compared to where it would have been otherwise. Okay? So what controls that shift? Well, there are a couple of things. So we have to see what is the change. What we are interested in is the change of momentum. So this was the original momentum of the electron, and this is the delta p. We want to see what is the change in the momentum of the electron in this process. So what does that? What is the change of the momentum? Classical physics, classical mechanics. Second? M delta V. Well, yeah. So that's the definition. But what controlled it? That's what controlled it. It's second law, Newton's second law, right? It's delta P is what? dP dt is what? That's another way of writing. That's a better way of writing Newton's second law. F equals ma. Force, yes. And if your mass is constant, then this becomes ma. If mass is constant, right? But this is the more general statement of Newton's second law. So delta P then is really integral of f dt over the period of time. So it's, let's say, from 0 to tau c on average. But there's one good thing here is that the force is constant. This force that you're interested in, let's say the electric field is constant, it's constant, right? In that period. So this is basically, by the way, what is this called? What is this integral called? Do you know? In physics? The impulse. The impulse, yeah. This is called the impulse. So this is f delta t, really. More accurately, f. Right? Does that make sense? So that's a change in the momentum. But that is basically, as we pointed out, is m, well, it's really m star because it's the effective mass. It's moving in the lattice. Delta v. Change in the velocity. So but is that true? It's the change in the velocity, that's true. But then what is the average velocity associated with this movement of electrons on top of this random thermal movement? So you have this very fast random thermal movement, but then due to this electric field, I'm slowly moving this electronic gas to one side. Right? What is the velocity associated with that? Let's call that the v drift. How is that related to delta v? On the average. And again, this is an approximate calculation anyway. What is it? Any thoughts? here and delta V here. So it's really the average of that, which is basically 1/2 of delta V. So what I can say is that delta V is F divided by F tau C over M, so this would be F tau C over 2M star. And what is F? What is the force? In this case. It's due to this electric field, right? So it's minus QE. So this becomes minus Q tau C over 2M star E. Now, this quantity, which is a proportionality factor or constant between the electric field and this component of velocity, drift velocity that's induced by the electric field, is called the mobility. Well, this without minus sign actually. This is the mobility. This is mu n. This is minus mu n E. So since we're talking about the electrons, I'm showing it as mu n. And you can do a similar thing with a different effective mass for the holes. Now, the holes, we argued like the bubble and the, do you remember the bubble and droplet discussion? So the bubble moves, it's kind of chunkier, right? It doesn't move as easily as the electron or as the bubble. So it has a larger, the hole, that's another way of saying that the hole has a larger effective mass. Now, if the hole has a larger effective mass, what can you say it's about the mobility? What can you say about the UP? It's going to be smaller, yes. So, that's an important relationship. It says that this component of motion, this drift component, which is a very slow perturbation on top of this really fast motion of electrons due to the random thermal movement, is proportional to E, the drift velocity. The velocity is proportional, and the proportionality constant is called mobility. At low fields, this is constant, because you can see it doesn't depend on the field. Right? There's nothing that depends on the field there. Now, this is interesting, right? Because think about it. If I had an electron in free space and applied electric field to it, what would happen? What can you say about its motion? Equations of motion. I can write this, right? So I would have something of this sort for the acceleration, not the velocity. So it's really the acceleration that would be proportional to the electric field. But inside the lattice, because of this overwhelming thermal movement and constant randomization of the direction of motion, what you actually get is that in fact it's the velocity that becomes proportional to the electric field, not the acceleration. That would have been the case for a free space electron. Does that make sense? Yeah? Any questions so far? Okay, but so, this is the thing we care about. So, we have this relationship. So, this is a different mode of motion, right? It's something that's induced through the application of the electric field. That's called a drift. Okay. Oh, exactly. And then, so then you have this drift. So then the question is, what can I do with it? Well, it seems to tell me, allow me to calculate what my conductivity or resistivity is. Because that was the objective when we started this discussion of semiconductors, right? We said, we start with the resistivity, we started with the macroscopic view, we said, well, okay, it's kind of an arbitrary quantity and all this stuff. We said, well, this is semiconductor, this is conductor, this is insulator. But now let's see if we can actually calculate the conductivity of any kind of material, let's say semiconductor in this case. So let's imagine a slab, this is the same slab that we have before, a slab of, let's say, semiconductor. And let's say an electric field is applied, external field applied to it. So, and then you have electric field, right, inside. And let's say you look at a cross section somewhere here. And you want to see how many electrons, on the average, cross this cross section at any point in time. So let's say the area of this thing is A, right? density of electrons is n. An n that we have. So the number of electrons per unit volume. Now, how many electrons pass through this? If I have an electric field E, what is it? Well, I have to see what is the unit of volume that crosses this space in unit time, right? So in time delta t, let's say delta t, I want to see what this delta x is. On the average, how much does electron move? So delta x is delta t times the velocity, which is the drift velocity. That's the part I care about. That's the one that causes net current flow, right? So this delta x. Now I want to get the volume of this little slice, because those were the electrons that crossed the cross section in that time period. And to get the volume, I have to multiply by A. And then I have a volume. I have the density per volume. So I get the number of electrons that crossed. And then I want to get the charge, so I know the charge per electron. This is the electronic charge. Or Q for sure, right? That's the amount of charge, delta T, that's crossed in delta T. So what is my current? I is delta Q, by definition. This is of course average, delta Q over delta T, which is minus Q N A B D. Or the current density, J, which would be I divided by A, or a uniform current distribution, would be minus Q N B D. But now I know the relationship between VD and the electric field. Right? What is that relationship? It says it is basically there's another minus sign there for an electron, so the minus signs cancels. Q N mu N E. Now, I have a relationship between J and E. In fact, in general, this is a vector relationship. I just derived it for a special case, but in general, I can write it like this. And this should be a familiar expression for you, right? What is this? This is Ohm's law. The microscopic form of Ohm's law. Just stated by length and the area. And what you get is basically V equals Ri, or 1 over Ri. V times 1 over R is I. So, what that tells me is that basically my conductivity is nothing but Q N mu N, or which is basically 1 over resistivity by definition. Well, is that true? Is that completely true? Is calculation completely true so far? I mean, is it accurate? It is correct, but I've missed something. I've missed another component of the current. What is that component?
Holes.
The holes, right? I just assume that all of my current is carried by the electron. So this is really not I, it's IN, and this is JN. Now I have a similar component for JP. I can write JP is, and you can do the similar thing as Q, P, the number of the density of poles, mu T, E. Now the total current, therefore, is given by J total is Jn plus Jp, which is Q times N mu N plus P mu P times E. And in general, again, this is a vector relationship. And this is my sigma. So 1 over rho, which is by definition sigma, is Q N mu N plus P mu P. And interestingly, we've been able to arrive at the resistivity or conductivity from a completely microscopic perspective. What we could measure at macroscopic level, we could also arrive at from a microscopic perspective. And that's interesting because it tells you that you can, if you know the density of electrons and holes, and if you know their mobilities and electronic charge, of course, you can determine its resistivity. And in fact, more importantly, now that we have access to doping, we have that tool in our toolbox, we can control these independently. So I can control the resistivity of this piece of semiconductor by controlling the number of electrons and holes through the process of doping. Okay? Shouldn't be that surprised. about this mobility concepts that we talked about. You see, the assumption here is that, the underlying assumption in this calculation is that this component of the velocity, the drift velocity, is very small compared to the thermal velocity, right? Because every time it hits something, it gets scattered, it gets completely randomized, and it gets absorbed into the thermal energy of the lattice. What if I keep making E larger and larger, the electric field is larger and larger, what would happen? Well, at some point, between two impacts, right, between two scattering events, what happens is that I can accumulate a lot of energy. And then, when I start hitting the next scatterer, whatever it's an atom or something, then what happens is that I am moving so fast, I've changed the velocity so fast that I've reduced the tau c. Right? If I accelerate this so much that the velocity increases, I should expect that it will hit something earlier. Right? When it leaves here, it starts accelerating and its velocity is much higher, or it gets an additional change in velocity that's comparable to its original thermal velocity, it's more likely for it to hit something earlier. Right? Does that make sense? If it's moving faster, it will hit something earlier on the average. So that means that tau c actually starts becoming smaller and smaller when E goes very high. It gets very large. So that's why you have this phenomenon, which is called velocity saturation. So what happens is that if you look at the velocity, the drift velocity, versus the electric field, initially it's proportional electric fields. And you can verify that to various means. But at some point, it plateaus. And for some other semiconductors, because of some other interesting phenomena, it can actually go down. So it peaks from gallium oxide, for instance, it has this non-monotonic behavior. But for silicon, it actually does that. And this velocity is actually called the saturation velocity. And the field at which it happens, it reaches 1/2 the maximum, is called exact. And these are quite important when we talk about short channel MOSFETs. We'll talk about them extensively. But think about it. In a MOSFET, you have a very large field because you can think about it. You have a 90 nanometer channel. And you're dropping a bolt across that. You can calculate what the electric field looks like. It's very large. And the velocity is completely saturated. Almost completely saturated in modern MOSFETs. We will talk about it extensively when we get there. But this is an important phenomenon. Okay? Alright, any questions on this? So now we can go to our next handout. This is the first part of it. There are two more handouts on, one more handout on device physics. So this is the first of the two handouts on device physics. And so what we'll do now, we'll start talking about how we can make devices by controlling the doping levels and what properties of the device. So we'll start with the PN junction diode, and then we'll talk about the bipolar transistor, BJT, and then we'll talk about MOSFETs. And in the process also we'll learn about other kinds of devices. Any questions so far about the mobility, the energy band gaps, and things of that sort, the solid state part of it? Again, it's very, very basic review of solid state physics. It's not intended as review, yes?
Does the temperature rise then when you apply an electric field?
It does. It does a little bit because you're basically taking energy out of the electric field and put it into the device, right? You see, think about it. If you have, it should, right? Because it's basically a resistor.
Right.
You're applying voltage across a resistor. So you get V squared over R kind of loss. That's where it goes. That's why the resistor heats up. Because it's a conversion of energy from the electric field, which is a low entropy source, into a high entropy source of the thermal reservoir, I guess. Yeah, good question. Any other questions? Alright. Okay, so now let's start with the simplest of the semiconductor devices, which is the PN junction diode. Well, So let's put them together and see what happens. So let's assume, so we are talking about PN junction. So the kind of junction I'm talking about at this point is so-called abrupt junction. So it behaves as if you make a uniform piece of semiconductor with p-type dopants, with acceptors, dope with acceptors. So it's a p-type semiconductor attached to an n-type semiconductor. The way it's actually made is not like this. The way it's actually made is that it's made out of one piece of semiconductor and you introduce the dopant atoms, and at high temperature, dopant atoms actually fuse into the semiconductor different ways, and that results in different doping profiles. So you can't really quite make a junction that's completely abrupt, but you can make things that are relatively close to this approximation. So a lot of things are approximations, as you can see. So if you have a p-type and n-type, and let's say you're at 0 Kelvin, at absolute zero, what do you have? Well, you have a vast number of silicon atoms on both sides, so I'm not going to show them. I'm not going to worry about them. But in addition to those, I have the dopants. So we'll talk about the dopants. Let's talk about the dopants and see how they behave. So let's say you have a so on this side, what you really have, you have column 3 elements, right? So when you go raise the temperature, what happens to them is you really have negative ions, negatively charged ions, with holes. So let me show those atoms as follows. So I will show them as, I have to do this once. Bear with me. These are my dopants. And I'll show them as negatively charged ions. And then at 0 Kelvin, I have a positive charge attached to each one of them, so all of them are neutral, none of them are ionized. Sorry. Okay, so they're not ionized. And the same thing on the other side. So on the other side, similar situation is this, where you have positively charged ions, the acceptors. Yeah, it's probably as boring for you guys as it is to draw these. And electrons. We'll have some green electrons. And they're all attached, so none of them are ionized. Okay, so good. So at 0 Kelvin, that's what you have. That's what we have. How about energy band diagrams? At 0 Kelvin, there is no electric field, there's no potential difference between the two sides, so the energy band diagram looks flat. The Fermi level is in the middle. Yeah, so this is EC, EB. And then of course on one side you have these, so this is the junction. On this side you have the p-type, so you have energy levels down here. Acceptor energy levels. And then you have donor energy levels here. So this is EA and that's ED. Right? Nothing exciting so far. Now, I raise the temperature slightly. What happens? As I increase the temperature, what happens is that we know it's easy to knock these holes and electrons off, to ionize these guys. We made that calculation before, right? So as soon as I raise my temperature a reasonable amount, I some of them are locked up. So one, and there, and then they will be free. So roll around. So get one here, one there, one there. Okay. Now, what do? They move randomly around, right? Due to the thermal movement. So, and there's a probability for them, for the electrons from this side to end up on the other side at some point. And the same thing for these guys. These guys randomly move on to the other side. So, what happens when they move to the other side? When they move to the other side, they become minorities, right? Because, for instance, when the electron moves to the other side, the deep side, there are a lot of holes, but it's a single electron. So its probability of recombination goes up substantially. There are a lot of holes to recombine with. So what happens is that, as a result, close to this junction, you start depleting these charge carriers. Right? So you get less and less of them because they have a high probability of recombination there, because that's where you have, on one side, high electrons, a large number of electrons, on the other side, large number of holes. And gradually, you start depleting them. So by the time you're at room temperature, or close to, I mean, it doesn't even have to be room temperature, close to it, what happens is that all of these are ionized, so all of them are free to move around, and you have a lot of free electrons and a lot of free holes. So what happens is that, effectively, you have a region close to the junction where you have very few electrons and holes. It's not zero, but it's so small that for all practical purposes we assume it's zero. And that's called the depletion approximation. You can actually do this analysis without this approximation. It becomes a lot more messy and it gives you the same result at the end. And if you're interested, I can give you a reference where you can go and look it up. But for all practical purposes, it's fair to assume that there are no electrons or free electrons or holes in there. And the other ones are also free. So you're moving around freely, and the same thing here. So with all these holes and all these electrons here. How about the energy band diagram? By the way, what happens? Well, now look at it. What do I have in the depletion region from a purely charge standpoint? I have positive charge on one side, it's positive ions, and negative ions on the other side, right? What does that do? Creates an electric field. So, which way is the electric field pointing? To the left. Right? Okay. What does that electric field do? Does it impede or facilitate the movement of additional electrons and holes to the opposite side? It impedes, right? Because if the holes want to go this way, they'll bounce back, and if the electrons want to go that way, they will bounce back. So that's how an equilibrium is reached. That's what opposes this huge thermal velocity. And it's an average process. It's a statistical process. It's not that nobody can cross. Fewer people can cross. Fewer electrons and holes can cross. And also they're balanced by the ones that are generated here inside. Because you still have random thermal generation, right? Every so often you create an electron hole pairs here. What happens if I create an electron hole pair here? Let's say one of the electrons is hot enough to create it to jump up, and then I create an electron hole pair. So I have a hole and an electron all of a sudden. Where would they go? Due to the electric field. What does the electric field do to these guys? Where does the hole go? It's pushed back into the P region. Right? Where does the electron go? That way. So you can see that that process opposes the movement of electrons and holes to the other side and compensates. So in steady state, the number of electrons and holes that have enough thermal energy on this side to be able to cross this energy barrier is equal to the number of electrons and holes that are generated thermally here and are pushed back to the opposite side. And that's why there's no net flow of current. So how about the energy band diagram? How does the energy band diagram picture look like in that case? Well, what happens in that case is that, of course, you have a bending in the band because the energies have changed. side, and that's your N side. Okay? By the way, which side is at the higher potential? The P side or the N side? Electric potential. The N side is a higher potential, right? But why is it shown at the lower energy level on that side? This is energy, of course. Why do I see lower energy here than there in this picture? It's very simple. It's electrons charge being negative. So this is the energy level for electrons, which is the electronic charge times the electric field. And electronic charge is negative. So that's one thing you should be careful about. These energy band diagrams are kind of always opposite of what your electric field corresponds to, because the electron happens to have a negative charge. Ben Franklin got it wrong. I mean, he did a lot of great things, but this one got wrong. He had no way of knowing, of course. So this is the thing. Now, you have this electric field, you have this energy band diagram, and what I said can be shown in a different way. I have a lot of electrons here, right? And if I look at my distribution of these electrons, the energy of these electrons, it kind of looks like this. So it's just basically the tail of that Fermi-Dirac distribution, which could be approximated with a Boltzmann distribution, right? So there are still few electrons that can cross. The ones that have more energy than that, these guys can cross freely, and the ones that are below are bounced back. Right? Same thing for the holes here. So if I look at the distribution of my holes here, again, there are a few of them that can cross, and the rest of them are bounced back, because they don't have enough energy to cross. And of course, as we said, these guys are compensated by the ones that are generated here, electron hole pairs. So when an electron hole pair is generated, this is what happens. Right? So an electron jumps from here to there. You have an electron, and you have a hole, and the electron will go which way? Would go down, and the hole would go this way. Right? Because for holes, the energy picture looks the other way around. Okay, so that's for the junction. Again, it's fine. It looks like something happens in there. There's some built-in potential. And by the way, we show this energy built-in potential as Q psi naught. So psi naught is the built-in potential, electric potential. So Q psi naught is the built-in energy difference, or the energy barrier height. Okay, fine. Again, it's not very interesting and exciting as is. And of course, we can calculate this psi naught, by the way. I think you're asked to calculate it. It's very easy to calculate. You look at those two equations we had for N and P in terms of Ni and the difference between the two sides. And what you do, you realize that at room temperature, what is N on this side? What is N at room temperature? Well, so this is the P side. I'm sorry. P. P is Na. Yeah. And N is Nd. Right? Because they're all the ions. So remember that we had this region in the middle for over temperature, where they were constant because they were all ions. Okay, so this is fine. But now let's apply some external electric field to this thing. I will apply what we call this forward bias. I will apply a positive potential to the P side and negative potential to the N side. What happens from a band diagram picture? If I apply positive potential to this side, what does that mean? Do I push it up or pull it down? Remember, this is the energy level for the electron. Positive potential here is, I pull it down because it's lowering the energy level for the electron. This has negative charge. Everything has a minus sign. So I lower the potential barrier. And what I do here, I basically, is as if I introduce more holes here, introduce more electrons on this side. So if I introduce more holes on the left-hand side, and more electrons on the right-hand side, what would I do to the depletion region, statistically? Yes, because there are more electrons and more holes here, so there are a larger number of them that can cross, so basically, effectively, this depletion region will be smaller, thinner. Right? Okay, and in energy fan diagram, what I've done effectively is to lower the height of this barrier. And this one. By how much? Exactly, if this voltage is VD, by QED. Now what happens? If I lower this potential barrier height, now how many electrons can pass? Which electrons can pass? Well, I have these electrons that can pass, right? These guys could pass before, and now they can pass too. But now I have a whole bunch of new ones can pass, who couldn't pass before. So lower the potential barrier, I made it easier for them to move, and just because of the random thermal movement, nothing fancy is happening. They're moving randomly, and many of them, they constantly hit the potential barrier and they're bounced back. Now I lower the potential barrier, more of them can go through. How about the holes? Again, the same deal. So now, these guys can go through too. Who couldn't go through? Now, but are they canceling each other in terms of the net current they're generating? Or are they adding to each other? They're adding to each other because I have negative charge going left and positive charge going right. Both of them correspond to net current flowing to the right. So that increases my total current. But let's focus on the electrons. What is the number of, so before, the number of electrons that could pass initially were these guys. Now I'm interested in calculating how much extra electrons can cross this potential barrier. How do I calculate that? Well, I have to calculate what is the number of electrons here. So that's simple though, because what I'm looking at is N with E greater than the energy, greater than Q psi naught minus VD, and smaller than Q psi naught. Right? But so this part is proportional to what? We have already done this calculation. You remember we did this calculation of what is the probability of, what is the number of electrons or electrons with an energy higher than an arbitrary energy level? So I can use that now. So this, I know is proportional to E to minus Q sine naught minus VD divided by KT. That's the energy, that's E1, right, that we had before. Minus the ones that could already pass even before I applied the potential, which is minus Q sine naught over KT. If I factor this term out, this would be proportional to, and I drop that factor term, E2 minus, the minus signs cancel, it becomes QVD over KT minus 1. Now, my net, and the same thing is true for the holes, right? That's also proportional to the same parameter. So if I take both of them and make a proportionality factor, I can calculate the total number, the amount of charge, and then the current that flows. So the total direct current is this proportionality factor IS times E to QVD over KT minus 1. And this should be a familiar equation for you. I'm sure if you've looked at diode equation, that's the expression that describes diode behavior, forward junction, right? Forward bias. See, it comes purely from the random thermal movement of the electrons. There's nothing else to it. If you know the distribution, which is basically we assume that it's Boltzmann because you're so far away from the Fermi level anyway, that's Boltzmann distribution. That's nothing else. So it shouldn't be that surprising that you get this. And it shouldn't be surprising if I tell you a diode doesn't work at very low temperatures, close to 0 Kelvin. Doesn't work well. Because there's no random thermal movement. I mean, very little random thermal. But that's interesting, right? That's simple calculation. So it just looks at, you look at the ones that can cross. So all you've done here by applying this external potential is lower the potential barrier, and everything else happens very quickly by itself. So it's almost as if all the work is done by them. You just basically turn the switch and the electrons take care of themselves. Okay. Now, how about if I apply any questions here? V is negative, so let's say I apply something like that. What would happen in that case?
The depletion region gets bigger.
Exactly. So you apply this, and then you make the depletion region larger. And what happens in the band diagram picture? Now, instead of lowering my potential barrier, I have made it greater. So what does that do?
Lesser electrons will cross.
There are fewer. I mean, it's like building a wall on the border, right? That's exactly how it looks like. The humans are like that, right? They want to go in a different direction, and then you make it harder and harder, and fewer harder ones go across. And at some point, you make it so difficult, nobody goes. You make a 100-meter or 100, I guess, yard wall on the entire border, nothing crosses.
What about tunneling?
Yeah, that could be tunneling, that's right. It actually can happen. Yeah. So that tells you that if there's enough energy that will somehow cross. Okay, but so now you've raised the height of the potential barrier, and now there are even fewer. I mean, there are still some that will cross, right? But now, how about the other component of the current? The generation recombination, generation one here. Right? You remember the thermal generation? Because in this region, this is a piece of semiconductor, right? And it is at the same temperature pretty much as the rest of the semiconductor, so it's at room temperature. So every so often, you can release an electron from the conduction band, and put it in the valence band, and create an electron hole pair. And that always happens, anywhere. And when that happens, one goes this way, and the other one goes that way. So there is net current flowing. But which way is that net current flowing? The hole will go this way, and the electron will go that way. So there's net current flowing in this direction, right? That's a reverse current. Now, what is that reverse current? Do you expect it to change a whole lot from what it was when we were in equilibrium, that current that compensated the ones that crossed? Not much, right? I mean, the width of the diffusion region is increased a little bit, so there will be a few more, but ballpark is about the same thing, because as we'll see, the width of the diffusion region increases only as square root of the applied electric voltage. So it doesn't change that quickly, it's not proportional to this voltage. And pretty much if you make first order approximation, say, well, alright, so it's almost constant, so that component remains. But what is that component? That was the component that compensated this, right? This term. That's why we didn't have any current flowing when I didn't apply any external potential. Those two components cancel each other. Now, that component, if it's that component, so this same equation is valid. So basically, I say I reverse, it's approximately minus IS. And therefore, this equation will hold approximately both in forward and reverse bias mode of operation.